me and Lasha will talk about time series data analysis. So as you know, guys, tomorrow we have a datathon at DataFest. So we tried to concentrate on emphasizing the most important points in case you have to analyze the time series data. So very, very practical and hands-on points that from our perspective are important to start with the time series analysis. And as Mario already mentioned, actually there is no clear way and kind of recipe, ready-to-use recipe, which you can use to model any kind of time series data. Therefore, it's quite a challenging problem, and we will start with the simple examples, and Lasha will continue. We'll start with this. I will start with the simple recommendations and also with description of the simple models and some recommendations from my side, and also Lasha will continue with slightly advanced models where we have like LSTM, so he will talk more about that. So outline of our talk is the following. So I will talk about exploratory data analysis, which is very crucial part when we are talking about when we are trying to model the time series data. I will also shortly talk about the ways, the general ways how you can do the model identification and then also the prediction, forecasting of the time series data. What are the main approaches? So just to give you an idea how to deal with this data. Then I will talk about the linear regression. Everyone knows the linear regression, so I won't go there into details. I will just mention what is the baseline. So this is the kind of main point there. I will talk also about autoregressive models, how to evaluate the time series forecasting model, the ways of the evaluation of the time series forecasting model, and then I will also mention few links to FB, Facebook Prophet, and Neural Prophet, which are I think very easy to use tools and very good tools to do some kind of time series forecasting if the time series data is good enough. So let's start. So first of all, you will get lots of, when you will deal with time series data, we should know, right? What is the time series? What is the definition of the time series? So time series is the following. So we have a timestamp and with equal intervals, right? And basically, most frequently, we have some kind of measurements done in this in the moment of the time, right? So we have the timestamp and the value that has been measured or acquired somehow at that moment of the time. And then we have sequence of this data. Usually, if we are talking about different time series that might be related to each other, usually when we are talking about time series, we can think about forecasting of the stock price, forecasting of the stock prices in the market, or forecasting of the weather, or forecasting of the energy consumption or the load, right? So, and especially, and also we can also think about forecasting of the efficient usage of certain factory devices, right? So factory devices, these huge industrial devices, they have lots of sensors. Each sensor can perform certain measurement, and this measurement information can be aggregated. This information can be stored in different formats, and then we can have extra information like environmental information like temperature, humidity, solar radiation around this factory. And we would like to merge this information together, right? So, and then the problem might appear, right? So we might have different granularity of the sensor data. Under granularity, I mean the following. So we can have sensor data measurements done every 2 minutes, and we might have the weather information measured every hour, right? Now you would like to merge this information together. So what to do, right? So it's a challenging problem when you would like to put together many different types of and formats of the data. And usually the best way, the clear approach here is to use the timestamp, which appears in both sides, right? So if you want to succeed in that, then you might need to work on the data itself, on the raw data itself. And one very important detail that I would like to share with you as well. So once you will get the raw data, somehow you should keep them somewhere in the storage. Doesn't matter what platform you will use, somewhere in the storage, such that it will, and you should be sure that this data will stay immutable there. So it shouldn't be changed. So raw data should be stored somewhere in the where it will stay as it is, or as it was in the moment of provisioning. So and if you would like to quickly merge different time series data with different timestamps, right? You can easily use definitely pandas library from Python. So you can majority of the systems can extract data in the CSV format, so comma separated values format. And when you have this kind of values, basically you can easily read this data as a pandas data frame. And if you have several data frames, you can then merge them according to different criteria. So here I pasted very useful short and quick start tutorial that might be useful for you tomorrow during the datathon. And also I have mentioned, as I have mentioned, so you can use pandas data frame, and here's a clear example when you would like to merge two data frames according to the year and the company ID. So you are just simply writing this pandas data frame dot merge, and then you are specifying what kind of you are specifying the data frames that you would like to merge, and also the ways, the column names that you would like to use for merging, right? And as a result, you will get eventually the data frame where you will have the IDs, the company IDs that are mentioned there, only the year information, the names and the revenue, and also the salary and company ID as well, of course. So this is very simple to do. So once you have the CSV files, you can read them as a data frame and then merge them according to the timestamp. So it's quite easy to do. Once you do that, and you have the merged data frame, usually engineers, especially the beginners, are not saving this huge data frame. So if we are talking about lots of CSV files, hundreds of CSV files, the merging process can take some time, and it's not a good idea to, and of course the data frame will be saved in the memory, and it's not a good idea to keep this data only in memory. Immediately export it as a CSV file and store it somewhere. So merged data should stay safe. As Charles mentioned, he had some challenges when he was dealing with the data and also his analysis during his PhD studies. I had the same hell. So it's not easy to manage all your data properly and follow and keep the models and the data in a way that you could reproduce everything from the beginning to the end whenever it's needed. Especially it is important when you are preparing the paper, publication, or report to your customer, for example, right? So it's important to keep the track what you are doing as well, and save the results, intermediate results somewhere. So once you will have this data, so merged data frame, and stored, which will be also stored as a CSV file somewhere. Obviously, you might have some missing values in this data. So right, NAs, right? So there might be some missing measurements, some missing values from the weather, etc., etc. So missing values is a common case. And then you can use forward filling or backward filling functions from pandas again. So, and forward fill means that the values will be filled according to the previous value, and the backward fill means that it will use the forward fill means that it will use the next value, and backward fill means that it will use the previous value to fill the gap if there is an NA in the data frame. Okay, so let's assume that we have merged the data, we have filled the gaps, everything is more or less okay, and now the next step is plotting, because plotting is very helpful to understand your data. So first of all, box plots that you can see here, they're very useful to have the feeling of the values that you are dealing with. So how many outliers you have here, what is the mean value, what is the distribution, so what is the so what is the spread of the data, right? Also you can plot 2, 3 or more values together with different coloring, and then you might see some kind of patterns. So if you see some patterns in the time series data, it's already good. So it's an indication that you can do something with that data, and you can apply some kind of model and catch these patterns with the machine learning techniques. So visualization is the most important step for understanding the data, and also the next step is deeper look into the data values itself. So you are checking the correlation between the variables. For example, we have some temperature measurement in different locations in Georgia, and we have this heat map of correlations. And also we have relationship between the certain values that we are interested in, and also the temperature that is affecting this value. Here we have this relationship kind of metrics that are mentioned. That is very useful if you would like to, for example, predict this consumption of whatever doesn't mean. So here we are talking about the temperatures in this location and consumption of let's say oil in these regions. So why we need to do the correlation search? So if we are talking about, and we should definitely start with the simplest models, right? So if we can model the time series data with linear models, then it's good enough. So we shouldn't go beyond that and shoot the bird with the cannon, right? So we simply and to have the efficient linear modeling process to make it efficient, you should get rid of the correlated or related values, right? So you should keep only non-correlated or not that much correlated values or variables for the modeling. Why it is important? From the mathematical perspective, it simply allows the computation process to converge. So simply you will get the result. Otherwise, there is a high risk that you will get the linear dependent system, and then the corresponding system of the linear equations will not be solvable. So that's why it's better to get rid of the non-correlated variables and keep only correlated variables and keep only non-correlated variables that are not that much clearly in a relationship between each other. So in this case, what we have, just to summarize, right? So in this case, after this short EDA, so we have the merged data. So you can get the data from external sources, from open data platforms, which are available on the space agency portals, or there are lots of open data platforms that are providing also data about weather. And many other details that you can search for, and you can get this data. You can get some private data that will be provided to you by some third party or your customer. So then you are merging this data according to the timestamp, checking that you don't have the missing values, searching for correlations. You know which variables should be excluded, and you know what is the target, right? So in this case, the target is consumption, not the temperature. So we would like to do the modeling or forecasting of consumption of oil, for example, in certain regions in Georgia. So this is the end of the EDA section. So please let me know after the talk if you will have any questions about that. And now let's go to the ways of the prediction. So time series data to model the time series data is not an easy job, as it was already mentioned. So, but from the first sight, it might seem that, wow, it's very simple. So why? Because the models that can be applied to the time series data modeling processes can consume or can use only the target values. The target values means that the values that we would like to forecast, predict. For example, the currency rate, right? Georgian lari currency rate. So you can take the historical data of the Georgian lari exchange rate with US dollar, for example, for 3, 4, 5 years, and use this exchange rate, only exchange rate information, to build the model and forecast the exchange rate for tomorrow or for other days, for example, month ahead, right? So this is one way. In this case, we have the univariate time series modeling and forecasting process, right? So we have only one variable, but you can add to these variables many other variables. So besides the exchange rate, you can add, I don't know, exchange rate of other currencies against the Georgian lari, and also you can add environmental conditions like temperature, humidity, solar radiation, many other variables. I don't know, density of the transport in certain areas of Tbilisi, anything. You can add many more variables, and these variables are called so the name of this kind of, there is no common idea how to name these variables. Some of the researchers are call them features, some of them are calling variables, some of them are calling regressors, predictors, exogenous variables, so many of them. So, but the idea is that if you would like to predict the exchange rate of Georgian lari against US dollar, right? Anything else that is not the exchange rate of Georgian lari against US dollar can be considered as a regressor, predictor, exogenous variable, or feature. So that's the idea. So we have two approaches, right? So we can take the time series itself, single measurements, train the model on these values, and build the model and make the forecast for that values, right? Only. Or we can take more data, additional variables that are in synchronization, that are synchronized, well synchronized with our target values in terms of timestamps, of course, and then build more complex model and make the forecast. So these are two kind of general approaches. There is no other approach for forecasting the time series data. So what is the baseline, right? So linear regression is a very simple model, right? Algorithm. So what we are trying to do, let's imagine that we have these points here, right? So let's say exchange rate or the oil price or the gasoline price in Georgian regions, right? This point here, and we would like to approximate these points with the line. And the criteria for the approximation is that the distance between these points and the line should be minimized, right? So the sum of the distances should be minimized. So that's the idea of the linear regression. I won't go deeper in that. So you can use a linear model from sklearn. It's easy, straightforward. Here you just need to write how many lines? 3, 7 lines, and you have the model, and you can make a prediction, right? So it's very easy. But why we need to talk about the linear regression at all? So let's imagine the situation that you have to model some very complex time series data, right? And you are using some neural networks based or LSTM based, some very complex deep learning model or algorithm to train the model, and you got the results. Okay, so how would you know whether these results are good or bad? You need something to compare these results to, right? So the linear regression is this poor guy, kind of, that allows you to use as a baseline. So it gives you the results which are good enough for comparison, right? So if your very complex deep learning based model is performing worse than the linear regression model, then obviously you are doing something very wrong. But if it performs better, then you can already measure how much better it is. So maybe if your accuracy is like 60% for linear regression and your accuracy for the deep learning based model is 62%, then maybe it doesn't worth to invest time and resources in training the deep learning based model. Just use linear regression, right? So linear regression is very helpful. So it kind of draws the line of goodness. So you have the line of goodness, and you know that your model should not perform worse. So now let's go to autoregressive models. Autoregressive models are also linear regression based models, but they have slightly more and complex parameters, right? So, and these autoregressive models, they are also quite powerful. And my recommendation is to always try to use simple models like linear regression, autoregressive models, and then go to the more complex models and try out to invest your time and resources in training the deep learning based models, for example. So ARIMA and SARIMA. So SARIMA is a seasonal ARIMA. So I will explain later in the slides what does seasonal means in this case. So ARIMA is an autoregressive integrated moving average model, right? So autoregressive, we will have this in these braces, AR, and integrated moving average will be like MA, indicated as an MA. So, and both of them, ARIMA and SARIMA, they are based on the, so they are all kind of very similar to the linear regression models. But in this case, we have 3 core parameters for ARIMA and same for SARIMA. So it's P, so it's the order of the autoregressive term. Q is the moving average term, and this is the number of the difference. So that is required to make your time series data stationary. So what does it mean? What does the stationary time series mean, and why we need to make it stationary? So the thing is that, well, first of all, here I also wrote the definition of the stationary time series. So stationary time series means that if you have measurements for multiple years, and obviously you have some kind of, maybe you have some kind of trends. The thing is that autoregressive and autoregressive models are using this time lags between the measurements, right? So with difference. So it uses time lags of different lengths, time lags of different length of the measurements. And if these time lags are correlated with the measurements, then your algorithm might not converge. So we need to avoid this. We need to make the data stationary. And stationary means that statistical properties of this data, like mean, variance, and autocorrelation. Autocorrelation is the measure of correlation of the time series values and the time lags, are more or less constant over time, so they are not changing much. And here I also wrote the reason. So basically, reason is that we should avoid the correlation of the time lags and the values itself. And the way how to do that is very simple. So we can simply subtract the previous value to the current value, and in this way we can make the data stationary. So unfortunately, I can't go deeper, otherwise I will be beyond my time limit, because this is why we are getting, let's say, stationary data after subtracting is another topic, and it deserves certain slides to explain it well mathematically, but I won't go deeper because there are many tools that you can use right now for automation of this kind of transformation of the time series from non-stationary to stationary. So, and basically the D represents the number of subtractions that you need to do with time series values to make the time series stationary. So it's basically the number of iterations. Now let's go to the P and Q. So what are the P and what are the Q? So the P is related to the autoregression, right? And autoregression means that the next value that we would like to predict or we would like to calculate depends only on the previous values or the linear combination of the previous values, right? That's it. And Q is related to the moving average term. And in this case, mathematically, if we look to it, the moving average is the dependence between the next value and the moving average term means that it depends on the differences between the current and the previous, between the predicted and the actual values. Which is basically an error, right? The prediction error. So if you are taking the difference between the prediction and the actual value, so it's error of your model, right? So, and the moving average idea, moving average models only depend on linear combination of these errors. And pay attention to this these details. So here we have taken P. So here we have taken previous measurements, previous values, P times, right? And here we have taken the errors Q times. So we have kind of P number and Q number of parameters that we would like to take into account when we're building these autoregressive models. And ARIMA model, if we go in a very simple transition from this mathematical expression to the next one, is basically a linear combination of the current of the measurements and the errors, and we would like to understand how many values of the how many measurements we should take into account when we are building the autoregressive models, and how many errors we should take into account when we are building the autoregressive model. So we should identify P and Q values to have, so which will basically define the length of this linear combination. So that's the idea of the P and Q values. So if you have huge P and Q values, the complexity increases, of course, of the ARIMA model, and then you have also risk of overfitting. And it also defines how deep you are going in past, basically. Okay, I will now concentrate on the coding part. That will be helpful. Hopefully, if you would like to train the ARIMA model, you can simply use stats models. So it's scikit-learn it's library provided from Python. So here I have an example of drugs usage, right? And basically we are reading this CSV file right from the online source, and then we are defining here the model, right? So we have here many parameters. So we have here the values of the P and Q parameters, right? So in this case, we are telling to the model that we should start with value 1. So we should take one value and one measurement in past, not more. Then we are talking, we are saying how much, what could be the maximum value of the P and Q values, and then we are also telling what should be the criteria of identification of this of the parameter D, right? So we should also calculate the D, the number of subtraction to make the time series stationary. And in this case, we are using ADF, which is translated to Augmented Dickey-Fuller Test, which basically helps us to identify the value of the D. So you can do it also manually, so saying that we will use the Dickey-Fuller test is very kind of common, and you can keep it in your case. Then basically we are specifying one more parameter, that is seasonality, and in this case we are underlying it should be false, because we're trying to train the ARIMA model, not sarima model. In case of the sarima model, we should indicate that the seasonality should be true. Yeah, and the other parameters, I would recommend you to go, let's say, deeper if you are interested, and check what other parameters are doing, because this would be very useful. But these are the key parameters that I have mentioned to start training your model and tweak it somehow. And this is the result, this is the output, right? So it's trying to fit the ARIMA model with this parameter set. It starts from 1 and it varies from to 3, and it calculates the AKIK information criterion, right? So AIC is the information criterion that tells us the goodness of the model, and based on this information, the process itself automatically selects the best fit of best combination of P, Q, and D parameters, right? Here, this 3 to 1 corresponds to P, Q, and D parameters that we have mentioned before. These are 3 key parameters of the ARIMA model. Okay, so model evaluation. Once we have done that, so we can start model evaluation with this simple command, right? So just to plot all the key parameters that we would like to use to evaluate our results. So top left here, standardized residuals indicates the difference between the prediction and the actual value, and here you can see that the mean is almost 0 and it fluctuates not much. And here we have the histogram and the distribution of the errors as well. So, and the mean is 0, and the variance is not that big, which is good, which means that our model is performing not that bad. And we have then some other criterions that tells us how good basically our predictions are, how much they are deviating from the actual values, and the most important part is this one. So the autocorrelation or the autocorrelation plot or the correlogram plot, which is also very helpful to indicate if we have chosen the proper value of D. So this is very important. One of the key parameters of the ARIMA. Okay, so when we are talking about the seasonal ARIMA model, right? So we should take into account that we are, in case of the regular stationarity of the data, we are just subtracting the current value to the current value to the previous one, right? So we are just subtracting the neighboring values. But in case of seasonality, we should subtract, let's say, larger chunks of data to larger chunks of data, such that we could catch the seasonal behavior of the data, right? And when we are subtracting this kind of big chunks of values, then we are getting this kind of results. So all this repetitiveness that we have here, or this repetitive pattern that we have here, is basically vanished when we're removing the when we're transforming the time series into the seasonal stationarity, right? So this is the way how it looks like, and now we have. It means that we have included more information in our data. One very important detail also that I would like to mention when we are dealing with time series is the sign, mathematical sign, I mean, of the difference between the next value and the previous value. So this sign can be considered as an additional feature or additional parameter to our model if we're talking about multi-parameter models that helps to identify the trend of the change. So if the value is negative, So if the difference between the current and the previous value is negative, it means that the current value is less than the previous one, so it means the process is declining, right? So it's reducing, some measurements are reducing. So if it's positive, then it's growing. And you can also take so-called second order discrete differential, so difference between three consequent values that will help you to understand the speed of this change, more or less. And this can be also very helpful when we are trying to model the time series data. So in case of sarima, it's also quite easy to kind of auto-build this model. And in this case, basically, we are specifying that seasonality is true. The other parameters are basically staying the same. So, of course, sarima has, again, these three key parameters. And just one additional change is that we just need to specify that the seasonality should equal to true. And making the forecast with sarima as well as in case of arima is quite straightforward. So here we are specifying that we would like to predict for next 24 periods. It means that next 24 periods means that 2 years from 2008 to 2010, 24 months, right? Basically, the only thing that we would like to do to plot this is just to use this code here. And in this case, we are using just the predict feature of the trained model that returns the next values which are not included in the training data, for example. So we split the entire time series data into chunks just to measure the efficiency. I will talk about it also in the next slides. So just to check the efficiency of the model. So we split the entire set of the time series into chunks, let's say 80% for training and 20% for testing. And on this 80%, we're training the sarima or arima model. And for the rest, in this case, 2 years, we are trying to predict. And this is the 95%, so 1 sigma interval that is plotted here also for the predicted values, and it will be very useful in case you have the data, for example, for these 2 years as well, to plot the blue line here, just to understand whether it goes beyond this 1 sigma interval or not. So how to measure the accuracy of the time series model, right? So any time series model, not only arima, sarima, or any other. So we should use. Personally, I prefer to use mean absolute percentage error, which shows you the percentage, which shows you the error percentage. This is the best measure to have the feeling how good your forecast is. Root mean squared error or mean absolute error, simply they give you the values. So, and if you have huge numbers, like, I don't know, oil consumption or energy consumption for certain country, these can be huge numbers, right? Then it will be really hard for you to judge whether it's good or not. And personally, I suggest to use MAPE as an error metric. And you can also do the cross-validation with splitting the entire data into small chunks. These are the links to the Prophet, which is another approach for time series modeling. Now stage is yours, Lasha.
So because of we are already out of time, I'll be quick and briefly touch the theoretical points. As Erekle mentioned, the time series can be modeled as kind of regression approach, and regression is part of supervised learning, and because we can analyze and model it like supervised learning model, it's also makes them available to model with deep learning too. From deep learning, I've chosen to present you LSTM, long short-term memory networks. LSTM is a special kind of recurrent neural network I won't touch because of time its details. I'll just present how simple it can be done to model time series model and predict time series with LSTM. For example, I've chosen airline passengers data, which is open on internet, and just plotted it. Then because it's like time series data, it has only two values, the time period and passengers in thousands. And I've just plotted it, and we need to prepare this kind of data for model, so-called X part and Y part. And I splitted it as train part and test part. So here are functions in my notebook, and just using Keras to initialize model. Everything is in my notebook. So when it's pure LSTM, they call, and everything they call vanilla. And first one to demonstrate, I've prepared for you vanilla LSTM. And with vanilla LSTM, we prepare initialize model, compile it, then fit on train and train data, make predictions on test data, and plot it with real data. And this is our prediction with blue line. But I haven't stopped only one method, because LSTM has different kinds of it. For example, another type is stacked LSTM. Stacked LSTM is extension which has multiple hidden LSTM layers. In this case, I have another one, so it has two layers of LSTM in itself. And other things are almost not almost other things are identical. And here are so fit it, predict it, and building its plot. And besides this stacked and vanilla LSTM, there is bidirectional LSTMs, which is extension of which is also extension of traditional LSTM, and it involves duplicating first recurrent layer, like providing a reverse copy of the input to the second. It's more complex, but in theoretical way. But like for coding, just we can import it from Keras and initialize it, compile, fit, and build prediction. Build prediction. Just because we have these three models, as Erekle taught about error metrics, I've chosen three error metrics, and besides plots, plots are not enough to see accuracy of our models. And I have prepared this simple calculating scores functions, ran it for these three models, put output of its result. And as we can see, for different metrics, there are different advantages. For example, for my mean absolute error, stacked LSTM is better than vanilla, and bidirectional is better than stacked. And so best one is bidirectional. Also about MAPE, mean absolute percentage error. And we've also worked out another method for error metrics, which is a regression error characteristic curve. Regression error characteristic curve is a powerful tool for visualizing for visualizing results, and its it's generalize the ROC curves to regression. We know, most of you know probably, that ROC curves are for classification tasks, and for regression we use regression REC curves. And for REC curves, I've preferred demo version. I've generated polynomial data and built two models, linear regression and polynomial regressions. And to compare their results, I'll present you these plots. So here, when we are using ROC curves, we calculate area under curve. But in case of regression error characteristic curve, we calculate area over the curve, and the area over the curve is estimate of error, and the smaller the area over the curve, the better the model. And here is for linear version and polynomial version. This is for demo. And for our LSTM models, as we check the some metrics, error metrics, the bidirectional was better with error metrics, but for with regression error characteristics, stack the LSTM is advantageous to bidirectional.